today we're looking at a calculus video. We're going to find the derivative of a rational function. And in context, this rational function represents a distance equation. So the function is the distance at time t is equal to 10t divided by the quantity 1 plus t, where t is greater than or equal to 0, and d represents the position of an object at time t. So the derivative then of this equation or this function would be a velocity function, and we want to find the velocity of the object at time t. So that means we want to find the derivative at point A. And in order to do that, we're going to use our definition of derivative, which is the limit as h approaches 0 of d of a plus h minus d of a divided by h. In our numerator, which is actually going to be a fraction, we're going to replace the t with a plus h. And so for our first part, we're going to get the limit as h approaches 0 of 10a plus 10h, replacing the t with a plus h and distributing, divided by 1 plus a plus h. The second term, d of a, we're just replacing the t with a. So we have 10a over 1 plus a. Now this whole term here is the numerator of our difference quotient, and it's divided by h. And of course, dividing by h is the same thing as multiplying by 1 over h, so we're going to write it as multiplication. So we have two fractions multiplied together. In our first fraction, or difference of two fractions, we need to have a common denominator. The common denominator for each of those is 1 plus a plus h multiplied by the quantity 1 plus a. So our first term needs the factor 1 plus a. So we're going to do the limit as h approaches 0 of the quantity 10a plus 10h multiplied by the factor missing 1 plus a for our common denominator, minus our second fraction, the numerator is going to be 10a multiplied by the factor missing for our common denominator. So it'll be 10a times 1 plus a plus h, all over our denominator 1 plus a plus h multiplied by 1 plus a, and the whole thing is multiplied by 1 over h. Now comes the long step where we have to distribute, and the good news is after distributing a lot of these terms will add up to 0. So we're going to have the limit as h approaches 0, multiplying our two binomials. We have 10a plus 10a squared plus 10h plus 10ah. Our second term in this numerator, when I distribute, I'm going to multiply by negative 10a to 1, negative 10a multiplied to a, negative 10a squared, and negative 10a times h for negative 10ah. And our denominator we are going to leave in factored form, and the whole thing is multiplied by 1 over h. Okay, combining like terms, we have 10a minus 10a add to 0, 10a squared minus 10a squared, and positive 10ah minus 10ah, leaving us with just the term 10h in our numerator, 1 plus a plus h times 1 plus a in our denominator. This is still the limit as h goes to 0, and we still have our factor 1 over h. The h's reduce. So that leaves us with, to find d prime of a, we are going to have the limit as h goes to 0 of 10 divided by the quantity 1 plus a plus h times the quantity 1 plus a. And now as we take h to 0, this term will drop off and we'll have 10 over 1 plus a squared. And this is excuse me, this is the velocity at time t equals a. So this is our velocity equation. Okay? Now, at any time t, we can say then that v prime of t, for a being any value for t, is 10 over 1 plus t quantity squared. So now we want to graph our velocity equation on our domain. Our domain was t greater than or equal to 0, so we have just the first quadrant. Notice that our velocity is always going to be positive because 10 is a positive number and our denominator is squared, so it's always going to be a positive number as well. So we have just our first quadrant. We go by a scale of 1. When t is 0, v of t is 10. So we have at this point, when t is 1, our v prime of t is going to be 10 divided by 4, or 2.5. When t is 2, we're going to get 10 ninths. And when t is 3, we're going to have 10 over 16. And so our equation, our graph, looks like this. Starting at the point 0, 10, and continuing infinitely in the positive direction. So what's our range then of v of t? Well, notice all of our velocities are above the axis, the horizontal axis, the t-axis, and end right here at the intercept 0, 10. So my velocity is between 0 and 10. It's greater than 0, but less than or equal to 10. Now we want to find the limit as x is t. I should put these t's. V of t as t goes to infinity. So using our equation, the limit as t approaches infinity of 10 over 1 plus t quantity squared. Well, we know what happens with 1 plus a big number squared. It just stays a big number, so it's 10 divided by a big number, and that goes off to 0. And that makes sense from our graph. We can see that as t gets larger, our velocity gets increasingly closer and closer to 0. Okay, so our next question says, for any two values, x and y, in the domain of our velocity equation, if x is smaller than y, how do v of x and v of y compare? So if we were looking at 2 points, x and y, for our time for our velocity equation, if v of x, if x is less than y, so x is to the left of y, our velocity at x is greater than our velocity at y. This is a decreasing function. So v of x is going to be greater than v of y. Now, what are the intercepts? Well, we don't have an x-intercept because this does not cross the horizontal axis. I guess I should call these the t and the v of t intercepts, or the horizontal and the vertical intercepts. So our horizontal intercept, there are none, so no horizontal intercepts. And our vertical intercept, which is our velocity v of t axis, is 10. So our vertical asymptote, or excuse me, vertical intercept is 10. Okay. Now, just some terminology. There's a lot of different ways to indicate a derivative of a function. And all of these are equivalent, but perhaps used in slightly different contexts. So if we have a function y equals a function of x, then the derivative function can be expressed in the following ways. The first way is f prime at x. The second y and is y prime. The third way is dy dx. The next way is as a limit, as a fraction. the limit as the change in x goes to 0, or the limit as delta x goes to 0, of delta y over delta x, or change in y over change in x, and that equals dy dx. We can also write it as an operation. This is d dx of y. That is, we are doing an operation on y. We are finding the operation or the derivative of y with respect to x. So all of these represent a derivative of a function f. Okay, a function is differentiable at a if f prime of a exists. And it's differentiable on an open interval from a to b, that is from negative infinity to a, or from a to infinity, if it is differentiable at every number in the interval. And our theorem that goes along with it, if f is differentiable at a, then it's continuous at a. Okay? So it's really cool that if it's differentiable, we know automatically that it's going to be continuous. Our question is, where's the function f of x equals the absolute value of x differentiable? Well, differentiable means that the derivative exists at every point in the domain. We know that this function, f of x equals absolute value of x, is actually a piecewise function defined as the opposite of x whenever x is less than 0, and x itself if x is greater than or equal to 0. This function is continuous at 0. It's defined, and the limits from both sides are the same. But what about the derivative? What does the derivative look like? And we're going to have to look at each piece to see what happens for our derivative. So for our first piece, if x is less than 0, then f prime of x on that interval is going to equal the limit as h approaches 0. Remember, our rule is f of x plus h minus f of x over h. Well, the rule that I'm using for this first side when x is less than 0 is the rule f of x equals negative x. So replacing x with x plus h gives us the limit as h approaches 0 of the negative of x plus h, so negative x minus h, minus f of x, so minus negative x, all divided by h. Simplifying, we get the limit as h goes to 0. Our x is negative x plus x add to 0, so we have just negative h over h. So we have the limit as h approaches 0 of the constant negative 1. And of course the limit of a constant function is the constant function. So for our first rule, our derivative at x, if x is less than 0, is equal to the constant negative 1. Now that should make sense, because as we look at our absolute value function, on our left side we have a linear piece, and the slope of this line on the left side is negative 1. Now let's see what happens on the right side when x is greater than 0. So if x is greater than 0, our rule for f prime of x is the limit as h approaches 0. This time my f of x plus h is just going to be x plus h minus f of x, which is just x, all divided by h. And so we get the limit as h approaches 0. The x's add to 0. X plus negative x is 0, so h divided by h, which simplifies to the constant 1. And so the limit of our constant function is 1. So f prime of x is equal to 1 if x is greater than 0. Remember, we're approaching 0. So here we have a slope of 1. Again, for our graph, for absolute value, that makes sense because the right side of the absolute value graph has a constant slope of 1. Notice that the two slopes, the one from the left side and the one from the right side, are not the same. -1 does not equal 1. So the derivative from the left does not equal the derivative from the right. And so the function f of x equals the absolute value of x is not differentiable at x equals 0. The feature that our graph has that clues us in that it's not going to be differentiable is we have a cusp, which is an abrupt change in direction. And that's our lesson on some terminology about differentiable and continuity, as well as an example with a position function and velocity.